All right, hey, science folks. We're just going to look at doing a little bit of lesson 9 here. So this front page you should be able to fill out for the most part yourself. We've talked about fission and fusion. If you're not sure what those are, you can look those up. As far as the process, which one releases more energy? Fusion releases way more energy. We talked about that a little bit yesterday. Here's a couple of reactions that you should be able to go through, and again, I'll have the key on the board. You can take a look at those. All right, so for this part, you're actually going to have to go into Schoology, and there is a lesson 9 activity sheet. Okay, it's just basically this sheet and in a digital form. And if you scroll down, this right here is a link, and there's a link to these flashcards in Schoology. You click on the link, open it up, it has you make a copy, and then you're going to just separate the different cards into whether it's a chemical or a nuclear reaction, and then you'll go through and answer the differences and similarities here, and then answer these two questions about what's the difference in the masses and where do you think the mass is going. This last question, we're going to actually lead us into our next one. It's asking about what is the famous equation that relates mass and energy. Some of you maybe know this. I think a lot of you have, and once you see it, I think you'll remember it or have heard it before. Okay, the equation is Einstein's equation. It's energy is equal to mass times the speed of light. Okay, so E equals mc squared. This is energy. This is mass. And this is the speed of light. So there's a relationship between energy and mass and light. Okay, it's known as E equals mc squared. You probably heard of that before. Okay, and we're going to use that in our next part here. Okay, so what we're going to do is actually going to do some calculations. Okay, and so when we look at energy produced in these reactions, we need to know something about the mass and the energy, right? So we just talked about that energy from the E equals mc squared. Okay, so we're going to look at a couple different things. So I'm going to work through one of these and show you, and then I'm going to have you do the rest of them. Okay, and there's a little bit of math involved here. It's not super difficult, but it is a little bit of math, and you can kind of follow along and go back and watch it if you miss something. Okay. So the first thing we're going to do is we're going to figure out the mass that we have here, and it's something called the mass defect. Okay, so it turns out that when you actually calculate the mass of an atom, if you just added up the masses of the protons and neutrons, okay, it doesn't really equal the mass of the average. Okay, and so we're going to have to figure out what's called the mass defect. It's the difference in masses between what we think it might be and what it actually is. Okay, so and we're going to use this equation, right? And so the mass defect, we take the mass of the nucleus, which is the actual mass, minus the number of protons. NP is the number of protons. MP is the mass of a proton, which is listed for you right here, and times plus the number of neutrons times the mass of a neutron, which is listed for us right here. Okay, so we're going to try to figure out the mass defect in both AMU, which is atomic mass units, and kilograms. Okay, so let me show you how to do this. All right, and it's the same process every time. So first thing what I'm going to do is I'm going to figure out, okay, lithium. How many protons and neutrons does lithium have? Lithium is right here. So lithium is element 3, so it has 3 protons. And because it's lithium 7, that tells us we have 4 neutrons. Okay, so there's our kind of our starting protons and neutrons. Okay, now look at the equation. The first thing is the mass of the nucleus. The mass of the nucleus is this, 7.016, and we give you those. So we start with 7.016 minus, okay, the number of protons times the mass of a proton. So the number of protons I have is 3, and the mass of a proton is 1.007. Okay? All right, then we're going to add that to the number of neutrons, which is 4, times the mass of a neutron, which is 1.008. Okay, and we put those in brackets because this all goes together, and we're going to subtract from this. Okay. So if we go through and do just a little bit of calculations here, okay, so all we're doing is going to multiply 3 by 1.007. So 3 times 1.007 gives me 3.021. And then I'm going to do the same thing with 4 times 1.008. We've got to make sure we do the right one. So that's 4.032. Okay. Now if we add those two together, 3.021 plus 4.032, we get 7.053. Okay. So we're going to subtract 7.016 from 7.053. Okay, so 7.016 minus 7.053. All right, and we get negative 0.037. Okay, we got that right there. And that answer is in AMU. Okay, so that's what we call the mass defect. Now, what I want actually is, what is my mass in kilograms? So what I'm going to do to get kilograms is I'm going to take that number multiplied by the mass in kilograms of 1 AMU. So I'm going to multiply that number by 1.66 times 10 to the minus 27th. Okay? So we're going to take that number times 1.66. Remember, we got to do the EE button. EE minus 27. Okay, and I'm going to get negative 6.14. I'm going to round it to the third decimal place. Or I'm sorry, to the three significant digits times 10 to the minus 29th, and that's kilograms. All right, so there's my first part. Okay, this is known as the mass defect. Okay, and our equation's right there. Mass given, number of protons times the mass of a proton, number of neutrons times the mass of the neutron. You add those two together, take the difference, we end up with a negative number. Okay, so that just means we're off. Okay, so now what we're going to do next is I'm going to use this number. Okay, so we're going to use the 6.14 times 10 to the 29th, and we're going to figure out the energy. Okay, so I'm going to flip to the next page. Okay, I'm going to use the mass defect here, the negative 6.14 times 10 to the negative 29th. Okay, and again, I get this from previous page. All right, so we're going to use that number, and we're going to put it into Einstein's equation. Okay, E delta just means change. E equals mc squared. Okay, and this is my mass. So it's going to be energy is equal to my mass, negative 6.14 times 10 to the negative 29th, times c squared. And c is the speed of light, which is 3 times 10 to the 8th. And we're going to square just that number. Okay, so you're just squaring that number. Okay, and we're going to get a final energy here. And this is an energy per atom. All right, this is going to be per atom. Okay. So depending on your calculator, I like to do kind of my squares a lot of times first. So 3 EE to the 8th squared it's 9 times 10 to the 16th. Now, it always is that, so if you want to just remember and use that every time, okay? But that number is this squared, and then I'm going to multiply that by negative 6.14 EE to the negative 29th. And I get negative 5.53 times 10 to the negative 12th, okay? And that is in joules per atom. So that's how much I have per atom. Okay? So I figured out how much energy it is per atom. Okay? All right, one more step here, and I know this is a lot of math here, is now we're going to figure out not per atom, but we're going to figure out how much is released per mole. We're going to figure out per mole. All right, if you look at the bottom, we're going to figure it out per mole. Okay? So again, I'm going to take this number. Okay? So I'm going to use my number of my energy. So my energy is 5.53, that's a negative, times 10 to the 12th. That answers in joules per atom. Okay? And I'm going to multiply that number by this number right here, because this is how many moles, I'm sorry, how many atoms are in a mole. That's an Avogadro's number. So how many atoms are in a mole? So I'm going to multiply this number that I just got from the last page times 6.022 times 10 to the 23rd. Okay? So let's do that. So we're going to do negative 5.53 to the negative 12th times 6.022 to the 23rd, and I end up getting this number right here, which is negative 3.33 times 10 to the 12th, and that's joules, which is our unit of energy per mole. All right. Okay, kind of a lot there, right? So what we did is, just to kind of recap quick, is we figured out the mass defect using our equation here. Then we figured out the energy using Einstein's equation, right? E equals mc squared. We used the mass from the previous page times the speed of light squared. We got this number, and that's the energy or joules per atom. And then we use that number to do our next part, and we multiplied that by the number of atoms in a mole. All right? And we ended up with negative 3.33 times 10 to the 12th joules per mole. And that's our final answer. Okay? So what I'm going to have you do is practice that now. Okay, and I have a key on the board. You're going to go through and do that for each of the next three, for fluorine, iron, and uranium. Okay? And work your way through and get the final answer of how much energy would be in a mole, and then try to answer question number 20. Okay? So the goal is to finish lesson 9 in class today. All right? And again, I have the key on the board.